तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Some of the most important circuits that we need to design for FPGA ASIC implementations are arithmetic circuits. So, basic arithmetic circuits are add, subtract, multiply, divide and so on, and all these circuits are very computationally intensive, and therefore they conventional methods of approach will not be sufficient. We will have to go for what is known as pipelining, and we will explain in a minute what pipelining is, and before that let us see what we are going to cover in this lecture. So, this applications for arithmetic circuits are basically from the point of view of implementing DCTQ, which we will be covering later on in design applications, and whatever we require for that application we will be covering in the next two lectures. And to start with, let me also make a mention that I will be covering only fixed point arithmetic and not floating point arithmetic, for simple reason that fixed point arithmetic is much less complex, that is it takes much less chip area, and that is the reason why this has been more popular in FPGA ASIC implementation. And in the traditional approach, what we have is a process. This process can be a simple add, subtract or multiply, or a complex algorithm which is sum total of all the arithmetic circuits that we have just now mentioned. And this process, let us say for example it takes one of the processes takes 100 nanosecond. So, the question is how are we going to deal with speeding up the system? That is vital, because certain applications such as video scaling and video compression and the like of it are very computationally intense operations and requiring specialized algorithms to solve, and all this can be done in real time. That is to say, you can process a motion picture only if you can do the computation very fast, and the conventional approach will not help, will not take you anywhere near to real time application, and therefore the need for the pipeline approach. And before we go for the pipeline approach, let us see the traditional approach. For example, we have a multiplier, and let us say it takes 100 nanoseconds or little less than 100 nanosecond. Then what do? We apply, if it is a real time application, we need to apply input data and periodically, let us say with respect to a rising edge of the clock, and every positive edge of the clock you need to input data, and out comes the processed output here, and since the total process takes about 100 nanosecond, so you will get only 10 megahertz throughput, that is 1000 by 100 is 10 megahertz, and naturally 10 megahertz will be the clock frequency as well. That is to say, we can apply only input data every 10 megahertz, every 100 nanosecond. So if a multiplier takes this much time, and we can't do anything worthwhile as far as real time processing is concerned. So what we do is we adopt what is called pipeline approach, and this approach basically has advantages as well as disadvantages. The advantage is that the throughput increases dramatically, and let us say for instance you have only 10 megahertz throughput. So how about jacking it up tenfold? Say is there any trick we can play so that this throughput increases tenfold? Yes, there is, and the answer is the pipelining, which we are already mentioned about, and this is the greatest advantage that we have, because we can now process say video compression and rest of the applications of that sort, which demand high throughput, and otherwise with the conventional approach it was not feasible, and that is the advantage, main advantage, and you have to pay a price for that. The price is not very heavy, it is just increase of some area, chip area, in the sense that we need to have what are known as pipeline registers, which we will be seeing shortly, and because of those registers this chip area will increase, and in addition to this, even in the conventional approach, if you apply data, out comes the result only after this delay of 100 nanosecond. So this can this delay is still prevalent in the pipeline approach as well. We will see why it is so, and that delay is referred to as a latency, and these are the two disadvantages that we have, that is chip area and latency, but this is only a small price we need to pay in order to get very high performance in terms of processing speed. So now let us see what a pipeline is. See, as you all know, we have a pipe through which we run either water or oil and the like of it to transport from one place to another, and in order to bring about this, you have to switch on a motor and start pumping the oil or water, as the case may be, and once you switch on, you do not get the water supply immediately, it comes only after a delay, and that delay may be referred to as the latency here, and water flows or water or any other liquid flows through the pipe, and here in digital realms, instead of water we can assume a data being flowing into a pipe which is composed of not only process but also registers, and we will see in a minute how why these are separately indicated, and that is the analogy that we can draw for this digital pipeline, and water pipeline is the analogy, and here what we claim is, we mentioned earlier, is there any possibility of improving the speed, say, and we also mentioned that dramatically it can change, say from 10 megahertz speed of operation to 100 megahertz operation, just by pipelining and having the very same hardware, and how to do this? Say, let us say previously we had a single single process, it could be, or a multiple process. So this process can be simple add or subtract, multiply, or a combination of all this, or including even a complex algorithm which we may be needing for video applications, and what all we need to do is divide this process into some convenient small time consuming process. Say, it is a mere question of division of the entire process strategically, and let us say we have some 10 process, and each of these process roughly 10 nanoseconds or less than 10 nanoseconds. So if you add all this, it will amount to 100 nanoseconds, which is the same as this process, and what we are going to do is just divide this process 10 times. So, what we will have here is, if you do that, we will have process 1 less than 10 nanosecond, then process 2, here I have put 10. So, that means it is a dotted line implying that similar blocks are there for the rest of it, and ultimately it is process 10 here, and you would notice that immediately after a process you will have a register here and clocked by the usual system clock, and at the positive edge of the clock whatever is available as the process 1 result, and these are all intermediate results, that will be registered here. For example, whatever is registered here, with the arrival of the next clock, that will go into a similar assuming that this is process 2. So, it will go in process 2 will be computed, and when the second clock arrives it will be registered in the process 2, and so on. It travels in the same fashion that water flows over the pipeline, and so after several clock cycles you will get the output here. So, that means to say it has what is called the delay, or what we in pipelining process we refer it as a latency, and you would notice that in order to convey it through 10 registers you need 10 clock pulses actually. Suppose the clock pulse is 10 nanosecond, you need 100 nanoseconds latency, and at the end of which only the output starts manifesting. The advantage here is we can have a clock 100 megahertz now, because a total process, all this when you add process 1, process 2 up to 10, all will add up to 100 nanoseconds as we started with the traditional approach, and in this case we need to apply fresh data every 10 nanosecond, and the processing order for the same, and that is how you get a throughput of 100 megahertz, and this will be clear if you follow this processing order. We will look at time axis on the y axis here, and register contents at what point of time it would register different processes. So, for instance, at 0 time, let us say we have applied at the input data 1. So, we are going to apply serially one data after another. Say for example, data 1, data 2, in that order we are going to apply at every 10 nanoseconds at the input here, and once you apply here, the process 1 will start immediately getting processed, and after 10 nanoseconds that process will be complete, at the end of which we can register in the reg 1 here, and that happens only here, because clock will strike after this only after 10 nanosecond. So, at 10 nanosecond it not only registers in 1 the process 1, and this is the nomenclature for the data. For example, if it is data 1 and process 1, this must be interpreted as corresponding to the data 1. Data 1 was processed completely as far as process 1 is concerned, and process 2 will be done for data 1 at this stage here. In fact, it happens in between, but the actual process result is registered only with the arrival of the second clock, that is at 20 nanosecond, and when this happens, this data 2 which was processed in process 1 will be registered in register 1 here, and that is the reason why 2 has been appended here, and this one denotes the data 1, data 2, data 3, whereas process 1 pertains to the register 1, which shows the intermediate result of process 1. In this fashion, process 1, process 2 up to process 10 are all stored in register 1 through 10. So, naturally at register 10, if you examine the output, you will get the final result, and while this is happening, you will be at every instant of clock, you will be reading a fresh data, data 1, data 2, data 3, and so on. So, here at 100 nanosecond we have read data 11 and simultaneously processed process 1 corresponding to data, just previous data here, and previous data of this is processed in second stage, and so on it goes, and at the register 10 is available the process output of process 10, which happens to be nothing other than the data 1. So, that means to say we started the computation here only at 100 nanoseconds, this process has output here. This is nothing other than the final output as we have seen here, and this is the one. And naturally you start getting the first output only after 100 nanoseconds, and that happens to be the latency here, and that is how the data flows via the digital pipeline, so to say. And there are two issues in partitioning of any particular design. Normal conventional texts refer this as horizontal partitioning and this as vertical partitioning. We will speak in terms of the actual functionality. Say for example, we have an adder or any other data processing which processes, let us say 16 bits, and you can add two 16-bit numbers, and if you do that one, it will be time consuming, as we will see a little later. And a better way of doing it is you just bifurcate that 16 bits into two 8 bits and then add only 8 bits at a time. That will be faster than adding 16 bits, but you can pipeline here. You can start adding the LSB first, and then the second clock in the second register you can that is process 2, you can add the MSB. In this fashion you can distribute your entire width, data width in this fashion, and there is no hard and fast rule for such division. You have to experiment with it and then arrive at the best possible bifurcation or partitioning. And this is the partition by data width, and next is partition of functionality. The functionality is like add, subtract, multiply, etc. So in terms of these additions, you have to club all similar functionality together and partition accordingly. That is to say, add must be partitioned different from the subtract, and which in turn must be different from the multiply, and so on. And we have already described this data width. I will just read out, this will be the summary of that. Consider an example of adder subtractor. In this adder subtractor, we want to add 8 numbers, that is 8 signed input numbers, each of width 12 bits, and what we need is sum of these 8 numbers, and each notice is 12 bits here. And the conventional approach of addition subtraction uses all the 12 bits together, that is 2 numbers are taken and added with all the 12 bits as a single entity, and that is a poor way of implementing, because there is a propagation delay involved, and which we will see little here. Since full adders are used for implementation, the result is delayed owing to the propagation of carry rippling through all the 12 bits. So when you add 2 bits, it will generate a carry. That carry is added to the next second bit, and so on. The carry propagates. That is the reason why the whole adding process is quite delayed. More the number of bits, more will be the delay, and therefore the processing speed goes down. You can by bifurcating this data to lesser values, say half of that 12, say maybe 6 or 7 bits, and you can improve the speed. Even the usage of carry look ahead circuit does not help in speeding up the computation, since a large number of gates and inputs are required in this case. There are certain circuits which can compute carry far ahead of time. So disadvantage using such circuits are, and they have lots of gates to be realized, and each of these gates have a large number of inputs, and if you really do put it, test when compared to a ripple carry of the same width, and when you check it over FPGA platform or ASIC platform using Synopsys DC compiler, you will get figure which is far less when compared to even the ordinary ripple carry, and that is the reason why this carry look ahead circuit does not really help. And this is my practical experience. I have examined both in FPGA as well as Synopsys platform, that is for ASIC, and found that ordinary ripple carry itself is faster than the carry look ahead for the reasons listed here. Then what is the answer? The answer for this problem is to divide the data widths into smaller chunks and introduce pipelining. That is what we have discussed so far, and we also need to introduce pipelining in the light of the basic principle that we have considered for the pipelining. And a mention may be made here in the data width partitioning approach, all sub blocks do the same function. Say for example, if it is data width, so if it is add, it merely adds irrespective of what width, whether LSB or MSB you are adding. So it is basically the same function that is being done here. And partition of functionality is another category. This also referred to as a vertical partitioning. In this method, we partition in terms of add, subtract, multiply, and so on. So in this method, the function block is divided into smaller sub blocks such as add or subtract and so on. And in this type of partitioning, each sub block does a different function in general. So this is different from the previous data width partitioning, because it does a different function such as add, subtract, etc. In the add or subtract example cited, LSBs 7 bits are taken of the 8 numbers are added concurrently, followed by the addition of MSBs 5 bits along with carry from LSB addition in subsequent pipeline stages. This is to say, what we do is we take only 7 bits of LSB and add in the first pipeline stage and register it, and in the when the that is in the first clock pulse, and when the second clock pulse arrives, we take the carry of this LSB addition and then add it with the MSBs. So MSB in this case will be 5 bits, and that is why we say 5 bits along with carry from LSB addition. In subsequent pipeline stages we add that. And so the adder subtractor design is as follows. First let us have this pictorially here. So we have N0 through N7 as 8 numbers, and each of which is of width 12 bits as we mentioned before, and MSB is 11th bit. This is the MSB, and so is the case for all this, and it is basically an adder cum subtractor, provided you have signed addition. You can use 2's complement in this, which we will be seeing the funda shortly what a 2's complement is, and then finally emerges a sum here. And note that width has increased here. Why the width has increased, we can easily reason out. There are N0 0 through 7, that means you need 3 bits. If you are to add 2 bits at a time, you naturally need 2 to the power of 3, which is 8, and I mean 3 is the one we had to add, because 3 bits are causing this addition. So we will explain this little clearly later on, and as a result you will get whatever is 12 bits here, it will add by 3 bits. That is what you have here, and hence it result will be 15 bits, and that's its pipeline, therefore there is a clock here. So this partition of the design can be in this fashion. This an algorithm evolved by the speaker for the sake of DCTQ application, and here in this case we have 4 adders adding at one stroke, that is concurrently, and thereby speeding up the process, and also having pipeline registers internally. So these are all the clock inputs here. That means there is one register inside here as well as here, and this register will add N0 N1 LSB alone here, and register at the first register here when the first clock strikes, and similarly in parallel we will also be adding N2 N3 N4 N5 N6 N7, and with the arrival of the second clock pulse we will be adding the MSB together with the carry generated during the LSB phase. So out comes 4 results here, and we repeat this exactly the same thing here by 2 more adders in the second stage. This is the first stage, this is the second stage, this is the third stage, and once again there is a clock input here, and at the arrival of third clock what we would have done is we would have added LSB of these 2 here, and with the arrival of fourth clock we will be adding the MSB of these 2 inside and register here, and finally I mean 2 outputs emerge from this here, and you can find once again add in third stage here, and this addition is there is internal register once again, and the final output is not registered, and because that is the requirement for the DCTQ application, and how 15 bits will reason out right from here. We start with the 12 bits. When you add two 12 bits, it will generate a carry, that means totally 13 bits will be the result, and here also it will be 13 bits. So is the case here. When you add 13 bits, out comes 14 bits result, and when you add 14 bits to 14 bits, final output will be 15 bits. That is why 14 through 0 is put here. And this is how we pipeline. So you see that every function is divided, and LSB, MSB are basically performing that add operation, and in this case all of them are add, so you won't know the functionality partitioning, although functionality partitioning is also implied here. So LSB, MSB is treated inside, whereas the actual functioning we can treat it as this is one adder, this is another adder, and so on. So that is how different functionality is also partitioned. Therefore, this particular design has partitioning of not only data width but also the functionality. So let us know what a 2's complement evaluation is before we start on the code, and let us take a simple data of 8 bits here, and this is the data here. So how to evaluate 2's complement in a shortcut we will see here. In order to do this one, look for first one here. This happens to be the first one. So what you do is just duplicate all these numbers right of 1 including 1, and in the second step here this is already done. What you do is go to the other bits, invert each of the bits and put here. So that is to say, although we say as 2 steps, you can at one stroke you can straight away arrive right from here. So what all you have to do is look for first one 1 0 0 0, put it here, then look here, invert each of the bits right here. So it is actually a one step process. So this is an easy way of evaluating 2's complement. 2's complement is nothing other than inversion of each of the bits, the result is added with 1, and that can be done in a shortcut in this fashion. Sign can be extended by any number of bits without affecting the actual value. So here what we say is the MSB is a sign bit, and you can append this sign bit repeat any number of times, and thereby the actual value will not be changed. And extension means duplication of MSB. So for in this case 7th bit is duplicated as 8th bit. The 8th bit refers to actually 9th bit, because we start with a 0. So to illustrate with examples, let us consider -1. We will add 2 -1. So the result must be -2 in decimal, and when you add this here, it is simple addition here, 1 plus 1 is 0, and so on. So finally a carry will emerge. Ignore that carry. If you drop the carry and interpret this straight away, you can easily interpret as -2, because this is normal addition without regard to any sign, right. So by looking at the MSB, you can distinguish whether this is in 2's complement. So you can recognize this as a negative number, that is why you put a negative number here. And if you want if you evaluate 2's complement of this value, and out comes the magnitude. Let us look at the 2's complement. So we have to retain the first one here, and replace all this by 0. That means it boils down to nothing other than 1. So its magnitude is 1, and that is what we have put here, because the MSB is the sign bit, being 1 for sign negative sign we put here. Same is the case here, and same is the case here too. And if you take the 2's complement of this, you will get this as 1, all will become what okay, this need not be done, we are just merely adding here, and okay, we will see this is MSB is sign bit, so minus is there, and first one we encountered is this here, and we retain these 2 bits and make the other bits 0. That is the shortcut notation we have already seen. So this is nothing other than all zeros 1 0, which implies 2. So the magnitude is 2, that is what we put here, and similarly you can put for all these things -1 1. If you add the 2, it is mere simple addition without regard to any sign. So if you deal with 2's complement, it is a plain addition of binary numbers here, and you can see for 127 127 the final result is this. You can work it out yourself. So is the case for minus 128, 128, and notice that for this 2's this MSB is minus 1 minus here, and if you take the 2's complement it turns out to be the same thing, which is nothing other than 256, because this is in 9th bit here, 4 plus 4 8 here. So hence 256 here, and without the sign extension the MSB will be mistaken as a negative number for high positive values such as plus 254, and what we mean here is this 254 if you add here, you have already added here, and what will happen, it will result in 8 bits result, it will be 8 bits. See for example 4 here, 4 8 here, we have extended the sign, therefore there is one more bit here, and we have seen that by extension and no value is changed, and in fact we can have a look at this. So I will come to that after explaining this. So what we say here is, without the sign extension the MSB, that is 7th bit, if you just take 8 bit numbers, this is the MSB, will be mistaken as a negative number for high positive values such as 254. Why we say is, if it is 254 the number is here. So if you see this is the 7th bit as we mentioned here, you see it as 1 will be mistaken for a negative number, because that is what we started with. So this, instead of interpreting plus 2 it as at plus 254, the system will be reporting it as minus something else. So that is not a desirable thing, and hence the need for extension of the MSB to the next location, and that is why we have a sign extension. That is the meaning here. We will prove that by one of these examples. For example, let us see here, we will take minus 1. In this case you have 9 ones here. What if I have just 2 ones alone? Will it still be minus 1? The answer is yes. So that means to say I can duplicate the MSB, which is the sign bit here in this case, and any number of times I can duplicate, right up to infinity I can put 1. So even then the whole all ones would mean that it is only minus 1, and the proof is very clear. So even if it is infinity, the last will be a 1, therefore we recognize it as minus here, and now we start with this first one, we retain this one and invert all other bits right up to infinity. So which will be 0 for right up to infinity, all except the first bit will be 0, first bit will be 1. So magnitude naturally is 1 for indefinite number of precision there, and therefore it is a negative value and as well as the magnitude 1, and this proves that you can by extending the sign bit, which is merely duplicating the actual sign bit to the to one more bit extra, and that is how we have added and seen the results. So we will go into Verilog code for adder subtractor. Suppose we wish to add 12 bit numbers, 8 of them, and each of them is a signed number. In essence what we are doing is add or subtract, and this is our goal, and this can be realized in 2 different ways. One is you can feed the inputs serially and one after another. For example, we have 8 inputs, let us say here in this block diagram, which does the addition or subtraction, and we have only in serial adder we have only one set of inputs, and you will have to apply one after another here at every positive edge of the clock, and synchronous to the clock you will have to apply different numbers starting with n0. First we apply n0, then n1, n2 and so on right up to n7. So 8 of them we apply one after another. This is what is implemented in a serial adder. In contrast to this, we have parallel adder, in which case we can apply all the 8 inputs at a time at one stroke, and of course with reference to a positive edge of the clock, and these are all the 2 things that we have seen. That is, serial adder is one possibility, another is concurrent or parallel adder, and if you want very high speed processing, naturally you go in for this concurrent adder, where chip area is of great concern, we go for a serial adder. And let us have a look at this serial adder. We have basically 2 numbers added here, and in fact all the 8 numbers are going to appear through this input, whereas the accumulated result will be available in a register. Internally there is a register, and that is what is output here as sum. And since we have 8 numbers of 12 bits each, and we need to have 15 bits totally, and the difference note is that 3 bits between the input and this one. This is clearly arising on account of the fact that we have 2 to the power of 3 number of inputs. That's the reason why 3 bits extra are coming here. And when this sum is valid is indicated by another binary signal here. And all this transaction will take place only when enabled, that is when enable is high. So we can write a Verilog code for this particular application. It is basically a pipeline approach. Although it is a pipeline, we are not going to use very many registers, but a single register will do the job. Since we are going to merely accumulate the results, the addition of 8-bit numbers are accounted here as comment as usual, and it's a pipeline serial ladder design. Of course, Verilog code is what we are talking about, and it is in 2's complement. We will cover this 2's complement in greater depth when we take up the concurrent adder, prior to taking the concurrent adder. And the goal is to add 8 numbers 12 bit each, and it is signed, and you have to feed the inputs serially at n input that we have seen earlier, and it has basically 8 levels of pipelining, and this registering will happen at the positive edge of the clock, and out comes the result. There are 2 ways of expressing the result, either as a sum or as a result. The difference we will see what exactly they are when we as we progress further, and naturally it will have to be 15 bits width and in 2's complement, and this is going to be a registered output, and this is the module declaration for the serial ladder, and we give apt name here because it is a serial ladder. We give this name, and it is 12 bit and signed. That is why this name has been given, and you have to list all the IOs here, and here according to the block diagram we have already seen, clock, enable and n are the 3 inputs, and sum valid and result are the 3 outputs. Sum and result are primarily the same output. The difference is that this will happen only, the sum will be valid only for 1 clock pulse duration, whereas this result will be valid for 9 clock pulses, and that is the difference between the 2. And this is in fact while writing the code you do not write twice like this, either you restrict to sum here or result, you do not have to put both, and just for simplicity's sake, when we see the waveform to aid us to understand, both have been separated out like that. And once you have declared the module, you have to declare all the IOs here. Inputs are declared here, and clock, enable and n are the inputs, and note that there is no these are all single bit signals, and similarly the output, this is a single bit signal which is indicating when the sum is valid, and the final result is here, and the same result is also available as sum, and this is valid only for 1 clock pulse duration, and the number of bits that we are reckoning is also indicated here. For example, input is 12 bits and output is 15 bits. We have also to declare wires and registers. The wire as you know is actually the assign statements outputs. These are all the intermediate outputs that we need prior to registering later on, and you have a 1-to-1 correspondence between sum next, which will do the accumulation of the different numbers. For example, n0 emerges first, then this will be n0 after summing, and before prior to that one we need to initialize this to 0, and we will see that will be done only in this sum case, which is a registered case. As we progress we will see the difference, and we also have to keep track of the number of inputs that we have already processed. For example, we are inputting only n0, and then we need to upgrade a counter, and it will go right from 0, 1, 2, 3 and so on up to 7, and therefore we need 3 bits here in order that we may keep track of number of inputs that we feed here. And here in this particular design it is n0 through n7, which is actually 8 numbers, and therefore 3 bits are adequate. And we also need to declare sum valid, which is basically the same as this sum valid, and with a note the difference in spelling here. and this is an assign statement, that is why it is declared as wire here. And we also finally have need the computer sum, and that is 15 bits as we have already seen, and it is going to appear in the always positive edge clock block, and therefore it is declared as a reg. And so is the case with the counter, that is also in a positive edge clock, and this is only 3 bits in width, and this is also a register sum valid, which indicates when the sum is valid, and this is going to be valid only for 1 clock duration, and result is same as sum, except that it is going to be valid for 9 clock cycles. So that when we do the computation of next set of numbers of consisting of another 8 inputs, then we will be updating this, and this is the very first statement, assign statement, in order to compute the sum next, and this is done by using a mux, which you are already familiar, and enable is the one which will enable the computation of the sum. Actually, to start with, when we have n0 input, it will appear here, and sum is initialized to 0, which we will notice little later on. So, to start with, we should not forget to clear this sum, otherwise we will be adding unwanted number, and therefore 0 plus n0 will be n0, and this will be assigned to the sum next, and this will be registered only with the arriving positive edge of the clock next subsequent to this. And when enable is not high, actually 0 goes through the sum next. So, that is what we want, and this will be registered during the always block positive edge of clock, and similarly we need to update the counter, and for that we have a count next here, and this is once again derived from the enabled signal. If it is 1, then this also a mux realization, we increment the counter by 1 and then assign it to the count next, and this is basically a pre advancing of the counter or pre increment, and otherwise you initialize to 0. And next statement is the sum valid, and this is also an signal which is ahead of the actual sum valid, and which will be registered later on, and this is assigned to using an assign statement, and only when the counter is 7, that means to say all the 8 inputs are already fed, and when n7 is arriving, at that point of time we make the sum valid, because with the subsequent clock the entire computation is over, that is after 8 clock cycles, and only when that 7 is encountered, then this 1 is assigned to the sum value, otherwise it is going to be 0. For all the other clocks right from first to 7 clocks, naturally the 0 will be forced to this one, and only with the arrival of the count value 7, it will be made 1. And next is the always block positive edge clock, we are taking the final sum and merely assigning here. So, this is what is already computed, and we merely assign to the final output, which is sum, and similarly the count next, which was pre incremented earlier, is assigned to this count register, and this is for advancing the count. And naturally the sum valid which was assigned earlier is actually output to the register, and so here we have one more for the result. This is not really required in actual design, and this is only to make things clear, it has been put. And in this case what we do is, this is a parallel circuit to the other always block which we have seen, and we merely assign the result here, and depending upon the sum valid. Sum valid was will be 1 only with the arrival of the positive edge of the clock, which we saw here in this particular condition. This is positive edge of the clock here, and subsequent clock only that will be reckoned here, and when that happens, it is only merely to delay the final result by 1 clock pulse, and this actual sum which was registered in the previous clock edge will be assigned to the final result. And if not, if sum is not valid, that means it is not going to be valid from for a count right from 0 through 7, and it will be valid only for 7. So, only for 1 clock duration the sum will be assigned here, which is the final added up values of sum of all n0 through n7. Otherwise what will happen, the sum is not yet ready. So, what we do is merely whatever was preserved in the previous cycle, that is for previous set of inputs added, that only will be assigned here if sum is not valid. Is this clear to you? I hope so. This completes the Verilog coding. We are not going to have a look at the test bench because it is quite a simple thing. We will have a look at the concurrent adder subsequent to this one. Before that, we will just see summarize the simplified results. The result of synthesis is it operates at 138 megahertz, and this is the device used here, XC600, and various mux and other primitive cells used are listed here, including the I buffer, out buffer, and a number of LUTs. It consumes very little. So, for this device it is 0%, that means a fraction of a less than 1%, and place and route results for this is here, and you notice that gate count is quite low, of the order of 464 here, and JTAG gate count is also quite high, but for higher sizes it will come down, and the frequency now it reports is much higher, and the test bench for the serial ladder, I am sorry, I said that I will not cover this, that is also there. We will quickly cover the test bench here, and we need to initiate 10 nanosecond as a half period for the clock to run. This is the standard practice which we have been following throughout the course here, and we have to include the design which is the serial ladder, which we have just now seen, and this test bench will have to be declared as a module here. That is what we are doing here, and consolidate all the outputs here, and so we merely declare all outputs, then clock and enable and input n are all to be declared as register in the case of a test bench, which we have already seen a number of times earlier, and we need to invoke the actual design, which is serial ladder 12s, and we instantiate just one time and list calling ports by name, and that is what. And the next thing is we initialize and apply the actual stimulus or the actual inputs. For example, clock is initialized here, and first input n naught value is 0, and we are going to enable only at 20 nanosecond here, and then apply all the other inputs. For example, n naught is here, and this is n1, n2 and so on in this order. N1 is minus 1, notice this one, this is in 2's complement, and all these things are in different values. The last value is just a dummy thing, because last n7 value is this one, n0 value is this one, and every 20 nanosecond we apply, and the data we offset as we have done before, so that data is always ready when the clock strikes. And after this we disable for a while for just one clock duration, and then enable again and apply this second set here of numbers here, and you can just remember this one here, and finally after applying all these numbers for n0 through n7 we disable here, and after about 100 nanosecond we stop finally, and then we run the clock by toggling clock here, which is once again the same thing what we have already seen. This runs at 50 megahertz. This is the end of the test bench, and we will have a quick glance of what a serial comparison between serial ladder and parallel ladder. For a serial ladder, which we have already considered, you require 8 clock cycles for inputting the n0 through n7, whereas in parallel, in one stroke, one clock pulse you can do that. And similarly, the output will take 9 clock cycles, because we had to, after having input all the 8, we had to make the enable low for one clock pulse, then only the sum will be cleared, and that is the reason why one additional clock cycle is required. So naturally the serial ladder is much slower, of the order of 9 times slow. In other words, parallel ladder is faster by 9 times, and at the price that you had to pay in terms of chip area 6 times what you have here. And actually if you see the parallel concurrent adder, which we are going to see next, we will see that basically 7 adders are required. Although 7 adders are required, actually the chip count is only 6 times here, because optimization tool is doing a very efficient job there. And so also the JTAG count, and maximum frequency operation here is 174, whereas in parallel, which we will be seeing subsequent to this, it is almost close to that. This is not a handicap. and we will see the waveform here, and before we conclude this serial ladder. And here you can see that clock, enable, n, sum are all applied here, and this is the final result here, and we can see this. This is the first set of inputs. 0 is applied, then -1, 2047 and so on. You remember -1 was triple F there, and here it is the final result. 0 minus 1 is -1, -1 plus 2047 is 2046, and keep on adding like this. Finally, for the entire set you would have done. The last one, final result is 681 for the first set of numbers, and this enable, mind you, is going low for one clock pulse, so that the final result is clear. You can see that here the final result is valid only for this 681, is valid only for this duration. That is why the sum valid is going only for this, and we have also seen a result that is being registered 681, and it will be valid for next 9 clock cycles, which we will be seeing in the next waveform here. This is the second set of inputs that we are going to apply, and here what you have is 100, 200, etc. we have applied. You remember that 100, then 200, so result is 300, then plus 300, 600, and then 400, 1000, and 1500, and so on. Then 1600 here, 1800, then finally 2047, and so once again this goes high, sum valid goes high, and final result is available at 2047. You note that one. This is, if you take this timing, it is coming at 350 nanosecond here, whereas in the first one what we have seen is basically it is this is corresponding to 170. So 350 minus 170 is 180, each is 20 nanosecond. That means 9 clock cycles it has taken. So this proves that serial ladder is 9 times slower when compared to the parallel ladder or concurrent ladder, which we will be seeing next. Thank you.